To definitively distinguish between the S_NAR addition-elimination pathway, which passes through a Meitner complex, and the benzene elimination addition pathway, organic chemists rely on elegant kinetic and isotopic labeling experiments. Because a Meitner complex preserves the aromatic skeleton while a benzene intermediate introduces a transient, highly strained triple bond across two carbons, their experimental footprints are entirely different. 1. Isotopic labeling evidence, 14, text C, or 13, text C. Tracking. The most conclusive proof for the existence of a symmetrical benzene intermediate comes from isotopic labeling studies originally designed by John D. Roberts. The chlorobenzene 1, text 14, text C. Experiment. When chlorobenzene labeled with carbon 14, 14, text C, exclusively at the C1 position, the carbon bearing the chlorine, is treated with potassium amide, text KNH_2, in liquid ammonia, analysis of the resulting aniline reveals a near equal 50:50 split of the label between the C1 and C2 positions. Why this rules out a Meitner complex, S_NAR, in an S_NAR mechanism, the nucleophile must attack the specific carbon holding the leaving group, ipso attack. If the reaction went through a Meitner complex, 100% of the aniline would retain the label at the C1 position. Why this proves benzene? The elimination of text HCl creates a symmetrical benzene intermediate where the bond order between C1 and C2 is identical. The incoming text NH_2 nucleophile can attack either carbon of the highly strained triple bond with equal probability, yielding exactly a 1:1 mixture of aniline regioisomers, sine substitution. 2. Kinetic isotope effects. Key. Kinetic isotope effects measure how changing an atom to its heavier isotope, e.g., substituting hydrogen 1, text H, with deuterium squared, text H, or text D, alters the reaction rate, K_text H, K_text D. This revealing step, RDS. Case A, benzene mechanism key. Consider the reaction of fluorobenzene on O-deuteriofluorobenzene with text KNH2 in liquid ammonia. When bromobenzene or iodobenzene is used, the rate of reaction for the deuterated compound is significantly slower than the non-deuterated compound, K, text H, K_text D, approx 5.5. This large, primary kinetic isotope effect proves that the text CH, or text CD, bond ortho to the halogen is actively breaking during the rate determining step. This matches an elimination first, benzene, pathway. Note, for fluorobenzene, proton abstraction is fast and reversible, making the subsequent loss of the fluoride ion the RDS. In that specific scenario, no primary key is seen unless a weaker base is used, but the elimination step is still verified through deuterium exchange with the solvent. Case B, Meitner complex key. In contrast, if you run a classic S_NAR reaction, such as the nitration or nucleophilic substitution of 2,4-dinitrochlorobenzene with an amine, substituting the adjacent aromatic hydrogens with deuterium yields AK_text H, K_text D, approx 1.0, no isotope effect. This demonstrates that no aromatic text CH bonds are broken before or during the rate determining step. The RDS is purely the nucleophilic addition of the incoming group to form the anionic Meitner intermediate. 3. Substituent effects and regiochemical trapping. Further proof comes from placing a non-participating substituent, like a methyl or methoxy group, on the aromatic ring to intentionally disrupt symmetry. When O-chlorotoluene is treated with text NaNH2, text NH3, it yields a mixture of O-toluidine and M-toluidine. When M-chlorotoluene is treated under identical conditions, it yields a mixture of O-toluidine, M-toluidine, and P-toluidine. The formation of the meta product from an ortho-substituted starting material, or a para product from a meta-substituted starting material, is structurally impossible via direct addition elimination Meitner pathway. It can only be rationalized by the formation of 3-methylbenzene and 4-methylbenzene intermediates. Summary matrix. Analytical method. Observation for Meitner, S_NAR, observation for benzene. Isotopic labeling, 14, text C, 100% ipso substitution. Label remains on the exact carbon bearing the halogen. 50% ipso and 50% sine substitution due to a symmetrical intermediate. Primary kinetic isotope effect, text CD. K, text H, K, text D, approx 1, ortho, text CH, bond cleavage is not involved in the RDS. K_text H, K_text D, GG1, text CH, bond breaking occurs during or before the rate limiting elimination step. Regiochemical outcome. Rigidly single product. Structural geometry matches the original halogen placement. Multi-product arrays, rearrangements, dictated by the placement of the transient triple bond.